Problems. Well, we're going to finish up reviewing Chapter 8, Exam 6 today. Pick it up with number 29. Okay. Let's see. I want to get not much I can do about that. I'll read it from up there. So using these electronegativities, we're given carbon is 2.5, hydrogen 2.1, chlorine 3, oxygen 3.5. Select from the following group the molecules that fit the given statement. Okay, so probably should have put, rather than A through E, to be confused with an answer, I probably should have put like Roman numeral 1, 2, 3, 4. That would have been better. But the question refers down to the one, this molecule contains a carbon atom with trigonal planar geometry. For that one question, electronegativities don't matter, right? That's superfluous information. My guess is that this was preliminary information for a multiple set of questions. And I picked the one out that didn't need that information. So which one has trigonal planar geometry for a carbon atom? All right, so we got A, B, C, D, and E, right? All right, let's see, what's that first one? CH3, CHO. 3, CHO. I'll talk about that more in just a minute. We've done CO2 before. We can dispense with that pretty quick. Cl, C2H6, and none. All right, let's get rid of this one. We've done this one before. We know it's shaped like this. That's linear. Right. So that's not trigonal planar. This is linear. Simpler molecules. Let's do this one, where carbon is the central atom. In order to answer this question completely, you have to go through the process of Lewis dot structure first. All right, so carbon has 4 valence electrons. 3 times 1 is 3 of these, and chlorine has 7. Okay, so that's 14, right? I added up correctly. Carbon in the middle, then we're going to have hydrogen, 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 chlorine. So that's 8. And I think I can see where this one's going. 6 electrons. Can't put any more around hydrogens. 2, 4, 6. So there we have it. All of our valence electrons accounted for. And everybody's got an octet or a duet. So this carbon has what type of symmetry? If you have 4 groups around that carbon, that symmetry is tetrahedral. Okay, and since there are no lone pairs, the electronic geometry is tetrahedral, and the molecular geometry is also tetrahedral. So that's not it. How about this one? So this one has 2 centers. This CH3 is attached to, we would write it like this. Well, let's see. Let's be consistent. We have 2 carbons with 4 each, right? So that's 8. And 3 for that hydrogen, plus 1 for that hydrogen, and then oxygen has 6. So that's 18. 18 electrons. All right. The way organics molecules are written, this carbon is attached to that carbon. And these hydrogens are attached to this carbon. And then we have an oxygen and a hydrogen. Okay, 2, 4, 6, 8, 10, 12. And that gives us 6 more. So we start from the outside and work our way in. Hydrogens can't take anymore. So we put our 6 around that oxygen. Then we want to make an octet. with this carbon. It's only got 6 carbon, 6 right now. So we take 2 of those and make a double bond. Okay. Now that carbon has 1, 2, 3. 3 groups around the central atom is trigonoplanar. Well, that was true. Actually, we found our answer because this one says none. If we went ahead and ran this one, in the interest of time, I'll just say we go like this, and those hydrogens are attached like this. And those are both tetrahedral. So we found our trigonal planar. It's this carbon right here, or A. Okay. I would say if you're going to memorize anything out of this chapter, memorize what the number of groups relate to geometries. So you want to review that, or do you have that pretty well in hand? 2 groups around a central atom, linear. Now we're talking about electronics right now. So 2 groups around a central atom is linear, 3 trigonal planar, 4 tetrahedral, 5 trigonal bipyramid, and 6 octahedral. And then to do the molecular geometry from that, you draw that structure, and then you cover up the lone pairs if there are any. And that gives you the molecular geometry. Okay, so that was 29. Let's see if these work any better. I got away from these for a while. But since I got a whole bag full of them, I figured I'd go ahead and use them. Okay. Let's see, next one. Try 34. Of the following, which molecule has the largest bond angle? Okay. Let's see. A, B, C, D, E. First one is ozone. I think we did that one before. OF2, HCN, and H2O. And is there any more than one of the above have equally large bond angle? More than one, which means we got to do them all. Okay, ozone. 6 for this, 3 times 6 is 18 electrons. So we have an oxygen, 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 and that's 4 equals 14. So 2, 4, 6, 8, 10, 12, 14. Okay. Now, ozone is one of those that we have to resonate. So, but for determining bond angles and geometries, you only need one Lewis dot structure. And then the resonant ones will be equivalent to that in just a different arrangement, but the bond angles will essentially be the same. They'll just be on different atoms. So in this case, we have an octet there, we have one there, we don't have one here. So let's just arbitrarily take that one. Okay. So around that central atom, you have 1, 2, 3. That's trigonal plane. Like that. That double bond. That. So we could write it the other way, just be flipped over. The bond angle here is right there. Right? And trigonal planar bond angles are nominally 120 degrees. That's 120 degrees. All right, OF2. We have 6, and 2 times 7 is 14, so that's 20 electrons. So we put O in the middle because it's to the left of fluorine, right? The one that's toward the metallic side goes in the middle if you can't decide any other way. So that's -4. is 16. 2, 4, 6, and 12, 14, 16. Okay. We have octets around everybody. So around that central atom, you have 4 groups, which means tetrahedral. And tetrahedral would say oxygen in the middle, and we would put, let's go in the back and put 1 lone pair and put a fluorine out here and a fluorine out here. And that makes that trigonal base with the other lone pair out here. Now, if we cover up the lone pairs, well, the bond angle is 109.5 nominally. But we know that when we cover up those lone pairs, we get a bent molecule. But we still have that bond angle, only the bond angle is not 109.5. I'm sorry? Yes, right. It's closer to 107. Because you have those 2 lone pairs. It's kind of like water. But it's not the largest bond angle. That's what we're looking for. Okay, HCN. So that's 1 plus 4 plus 5. Yeah. So that's 10 electrons. So we have hydrogen, carbon, nitrogen. Minus 4, it's 6. Okay. 2, 4, 6. We did this one before also. We got to make an octet around that carbon. And the only place we can get it is here in the nitrogens. That gives us a linear molecule, 180 degrees. And we know water, we've done water so many times. It's like this one. 109.5, actually less than. So the largest bond angle is this one right here. A 180-degree linear molecule is the largest bond angle. That's the way you would do it if you didn't already know what those bond angles were from previous experience. If you already know what they are, then you can cut your answer time short quite a bit. See, I heard a ding or two. Zach and Josiah. Oh, yes. All right, let's see, where was I? 35? 35. Which of the following molecules is non-polar overall? So just as a reminder, what do we need to know to determine polarity of a molecule? 2 things. Are the bonds polar? Right? And then, is the molecule symmetrical? Right. If the molecule is not symmetrical and the bonds are polar, then you have a polar molecule. So let's see, A, B, C, D, E. Let's see how many of these we might have already done. We can shorten the time. SF4. Let's see, I'll look at this way. SF2. CCl4. H2S. And OCl2. The question again was non-polar overall. Well, I'll tell you what, we've done this one before. Carbon tetrachloride, it's tetrahedral, and each of those bonds is polar toward the chlorine. You would have, say, a chlorine here, chlorine there, chlorine here, chlorine there. We draw this base, and then the carbon would be in the middle, like that. So all those bonds are polar. They would be polar this way, polar this way, polar this way, polar that way. But they will be equal in magnitude and balance one another out. This is your nonpolar molecule right there. We could do the rest of them, but the rest are polar. This one's like water. That's definitely polar. I'd have to draw the others to prove it. But in the interest of time, we found our nonpolar molecule. Now, if I got sneaky and replaced one of them with a none of the above, then you'd be stuck. You have to do them all to be sure. Or two of the above, that would be worse. All right, 36. Okay. Which of the following molecules are non-linear? Okay. Looks like we've got some. All are linear, E. A, B, C, and D are pairs of non-linears. Okay, so it looks like we're kind of stuck. NO2 minus. C2, H2, N3 minus, HCN. Some of these we've done before, so we can knock them out pretty quick. And H2O2. All right. We did that one just recently. We've done this one before. So those are both linear. They don't satisfy. So it's that one, that one, that one, that one. We have to decide which pair because the answers are given in pairs. All right, how about this one? C2H2. Okay, it's 2 times 4 is 8, and 2 is 10. So we have this one, and that. 2, 4, 6, 8, 10. Whoa, hold on a second. What did I do wrong? 8. I put too many hydrogens in. That was the problem. Okay, 2, 4, 6. I have 4 electrons left over. 2, 4. Okay. In order to, that right? Let me redraw that. 10 electrons is right. C, H, 2, 4, 6. Okay, 6. 4 electrons. All right. So we have 2 here and 2 there. Okay. If we take these two and make a double bond out of them, that gives this one an octet, but not this one. So we have to take these two and make another double bond. Now they both have octets. Okay. That's acetylene, and it's linear. So we can't use this one, can't use this one, can't use that one. It's this one, this one, this one. So let's go ahead and look at this one. Do the ones with ions. Electron. 3 times 5 is 15 plus 1 is 6. 16 electrons. N. That's 2, 4, 12. 2, 4, 6, 8, 10, 12. Okay. So this nitrogen needs an octet. And it's similar to that problem we had before with carbon dioxide. Do you make a triple over here and leave that one single, or do you make a double? And the one that gives us the lowest array of formal charge is the one where we put a double on both sides. Like that. And this one has a charge. If we don't put the charge around it, then we're throwing one of those electrons out. All right, so this one's linear. That can't work. All right, so by process of elimination, we found that NO2 minus and H2O should be the right answer. H2O2. This is hydrogen peroxide, and it's going to be like this. This, that. Let's see. That would be 12, 13, 14. 2, 4, 6, 8, 10, 12, 14. That's it. It's bent. It's a double bent molecule. Okay, and this one, I think this one's kind of wonky actually. That's 5 plus 2 times 6 is 12 plus 1. So 18 electrons. I'm going to go ahead and do this one because it's a polyatomic ion, which is nitrite. NO. Okay, 1, 2, let's do 4. 14. 2, 4, 6, 8, 10, 12, 14. All right. So this one is going to have a resonant structure. That'll be one of them. And the other one will have a double bond on the other side. And of course, like that. Okay, so this has 3 groups in the middle, which means trigonal planar. Only cover this one up. Molecular is bent. Right. So this one and that one are the correct answer, which is C, right? C. All right, 38. Molecular structure, BRF6 plus. BRF6 plus. Okay, they're all halogens, right? We've got 7 halogens times 7 is 49 minus 1, 48. Bromine goes in the middle because it's below fluorine. 6. 1, 2, 3, 4, 5, 6. Fluorine. 2, 4, 6, 8. 2, 4, 6, 8, 10, 12. 36. 2, 4, 6. 6 times 6 is 36. We put 6 around each one, which would make an octet for each fluorine. It would also make an octet for bromine. And it has a plus charge. So what's the structure of that one? 6 groups. Octahedral. Right? Is that what you said? Okay. Don't whisper. Octahedral, which is C. Now we got 39. You do enough of these, you can do them as fast as I'm doing them. Trust me. Xenon octafluoride. Fluoride. Okay. Xenon has 8 because it's noble gas, 6, and then 2 times 7 is 14. So 28, right? 28 electrons. Now, who goes in the middle? When you have a compound made with a noble gas, usually the noble gas goes in the middle. So that's where I'm going to put it. And we have an oxygen, we have a fluorine and a fluorine, like that. 4, 6 is 22 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18. Which is 4, right? 4 left over. 2, 4. Goes on the xenon. So that's 1, 2, 3, 4, 5. So 5 means a trigonal bipyramid electronic. So the question is, where do those lone pairs go? If we drew the trigonal bipyramid like this, there's the base, and then you have xenon in the middle, and you have something up here and something down there. Actually, off center would be better. Like that. Because we're going to have something here and here. So in a trigonal bipyramid arrangement, where do the lone pairs go? On the triangle. Okay. So we would have, say, a lone pair there and a lone pair there. And the rest would be, well, let's see. Oxygen, I'm not sure where you would put the oxygen. I think the more electronegative would probably go here. And then the fluorines would go there. I mean, the more electronegative fluorines would go on the apexes and oxygen would go on the triangle. More than likely. But what, as the case may be, what's the molecular geometry of that one? Yeah, the molecular geometry. Well, I cover these up, and what you got left? You got a bond here, here, and here, which is T-shape. It's a T-shape. Okay. That one took some imagination. 44. Select the correct molecular structure of SiH4. I'm pretty sure I know what that is, because this is in carbon's family, which means it's going to have 4 valence electrons, 4 of those. So we're going to have 8 total, silicon in the middle. And there's all of your 8 electrons right there. That's tetrahedral. Okay, simple. Silicon tetrahydride. Actually, silicon tetrahydride is what we would think of as a systematic name, but actually, instead of it's analogous to that. An organic chemists call that methane. So if we substitute silicon in there, we're going to call this silane. And I think that's the accepted name for it. I want to call it silicon tetrahydride, but carbon tetrahydride would sound funny. So methane is that, silane is that. All right, 46. Another structure, BeCl2. Okay, so we got 2 times 7 is 14. Beryllium has 2, doesn't it? Yeah. Has 2 s electrons. So that's 16. And we have beryllium in the middle, fluorine on the ends, minus 4 equals 12. 2, 4, 6, 8, 10, 12. Now, as luck would have it, we can make octets for beryllium out of this. Like that. So it is a linear molecule. Now, if this was hydrogen, beryllium dihydride, it would be a linear molecule, but we could not make an octet for beryllium. It would be deficient. Although both of those exist, beryllium dichloride and beryllium hydride, both exist, but their electronic structures are different. $48. All right, xenon difluoride. How many pairs of electrons surround xenon, and what is the molecular geometry? How many pairs of electrons? Now, it doesn't say lone pairs or bonding pairs, so we have to count them all. That's 8 and 14 is 22. Xenon. You're here. And let's see, that's 18, 2, 4, 6, 8, 10, 12. Got 6 left over. 2, 4, 6. Okay. So if we've got 5 groups around the xenon, electronically speaking, that's trigonal bipyramid. So we're going to have this triangle, and we've got 3 lone pairs are going to be on the triangle. Xenon's in the middle, and fluorine's up here, and fluorine's down here. So it's a linear molecule. Okay. How many? That answers the second part of the question. First part of the question is how many pairs? Does it say pairs or how many electrons? Pairs. 1, 2, 3, 4, 5. 5 pairs. Okay, so that blows out of the water. Should have said lone pairs. That's a mistake. Because you could interpret it both ways. Let me make a note. 48. Should have said lone pair. Now, wait a minute. This is the key. I may have already made that correction here, just didn't do it on the key. Yeah, or does it say the same thing? That's the same thing. Missing a bunch of stuff. Jack Ray. This is missing a massive amount of information. So it means we copied. It was. Yeah. Hope nobody got one of those. Do you have, are you got the same numbering system up for now? Okay. Yeah. That one, the copy machine messed me up on that. Okay. Some goes. Crash. And back to 48. I need to make that correction. LONE, right? As in Lone Ranger. LOAN is go to the bank and get some money. Okay, 48. We're done with that one. The answer, if it was lone pairs, the answer would be 3. $49. Choose the member of each set that best matches the label. Okay. Which of these are more metallic? Beryllium or barium? The more metallic are the ones with the lower electronegativities because they're more likely to give up electrons. So barium is below beryllium. Barium should be the more metallic. Barium would fill in the first spot. Then the more covalent would be the one between a metal and a nonmetal versus 2 nonmetals. So the more covalent would be magnesium oxide, I think. Oh, no. I'm sorry. We're not, okay. I was thinking polarity. All right, the more covalent is the one that has two nonmetals versus a metal and a nonmetal. So that makes that one covalent. Okay. Now the highest electronegativity. All right. It looks like up and to the right, the furthest we go is oxygen. Okay. So those three would be E. Would answer that question. I have to read my own questions correctly. All right. Got a calculation coming up with 50. Let's see. Use the bond energies given below to calculate the enthalpy change for the reaction. Okay. So HCN and 2H2 yields CH3 and H2. CH3 and H2. All right. This one should be fairly simple. We have to know what bonds, because of the information we're given, we have to know what the bonds are. This one is HC triple bond N. Okay. We can leave out the lone pairs because they don't count. Not for this problem. This one is like that. Only we have two of them. And this one has carbon with 3 hydrogens on it attached to a nitrogen with 2 hydrogens. Okay. Now to complete this octet, that nitrogen has a lone pair. And of course this one does too. So now we know all our bonds. We take these, total them up, and subtract those. So we're going to have hydrogen carbon. Hydrogen carbon is what? 413? 413. And this is in kilojoules. So I'm not going to write those numbers in. So this is 413 plus carbon triple bond nitrogen, 891. And there's only one of them. Right? In this case, we have 2 hydrogen-hydrogen bonds, 432E. Okay. So that takes care of all these, right? 1, 2, 3. 1, 2, 3. And then we subtract. We have a carbon, we have 3 carbon-hydrogen bonds, which should be 413 each. And then we have a carbon-nitrogen single bond, which is 305. And then we have a nitrogen-hydrogen bond, 2 of those. Nitrogen, 391. There we go. You already calculating it for me? No? Okay. So 413, add 891, and 432 times 2, add that in. So I got 2168 kilojoules for this side. On this side, we have 413 times 3, and then 305, added that in, and 391 times 2. Add those in, I get 2326 kilojoules. Okay, so let's see, I'm just checking. I've got to make okay. So this overall is minus 158 kilojoules. B. Okay. All right. 51. Doing on time. I'm running short, of course. Pretty sure I'm running short, right? I got till quarter to Order 2. 145. All right, 51. Given the following information, calculate the change in enthalpy for this reaction. All right. 2 lithium solids plus 2 HBr gas. Yeah. And hydrogen gas. And then 2 lithium solid. Okay. So what we have here is another Hess's law. And I picked this one out. Now, 52 is the same type of calculation, only 52 is more cryptic because it uses abbreviations. So I'll do that first. S to gas, solid to gas is sublimation. That's the sublimation energy. IE1 is the first ionization energy. BE is the bond energy for dichlorine. And formation energy for rubidium chloride. So you have to know how to write that one. And then electron affinity for the chlorine. That's what those mean. Now, in this first one, this 51, you're actually told what each one is and given the equation for it. That makes it easier to deal with. All right. So, if we start at the top and say, all right, there's lithium solid, and lithium solid, that is the standard form of lithium. So, we're not going to have an equation that gives us this one. We're going to have one that uses that one. Because, let's see. We need to turn this into a gas first. Because, look at it this way. In order to form that one, we need an energy of a lattice energy. So actually, let's start with this one. The lattice energy for LIBR would be what? Lithium gas plus bromide gas yields lithium bromide solid. Okay. Well, we've got 2 of them. So which one is that? That's next to the last one, lattice energy, minus 809. So minus 809 kilojoules, but we need 2 of them. All right, to give us 2 there, 2 there, 2 there. Okay. So we've taken care of this one. In order to get to this position, we need to sublimate that lithium. Okay. We need to get to the lithium gas, and then we need to ionize it, but it needs to be on the other side. So that makes lithium solid on this side and lithium gas on this side, and 2 of them. So the value that sublimates lithium solid would be the first one, sublimation. So that would be a minus 166 now, times 2. Okay, got that one. Now we need to take this one, and we need to, let's see, hold on a second. We can't have this in the final equation. This is the target. So we've got to have this one on the other side. Lithium like that on the other side. Doesn't make any sense now. I'm sorry? Ionization energy, yeah. Lithium. Oh. Well, that was dumb. It needs to be on this side. That's why it doesn't work. And that's still plus. Okay, everybody see where I goofed? That one needs to be there. All right, now we're getting somewhere. This one needs to be, let's see. Yeah, ionization energy needs to fit in there somewhere because we need to produce this one. Actually, this one needs to be canceled out because it can't be up there. So that means this lithium plus needs to be on that side with this electron. And this lithium gas needs to be over here. But we need two of them. And that will cancel this one out because it's not supposed to be up there either. So the ionization energy is 520 times 2. And that is correct order, yes. 520, that's a positive 520 times 2. There we go. Okay. So we've taken care of this one and that one so far. Now we need, let's see. We need to get the bromine in there for this one. All right, how did we end up with this bromine? Well, bromine needs to go on this side, bromide, I should say, on that side. And the electron needs to be on this side. Actually, that's 2. And this is 2. This is 2, because that's 2. And the bromine gas is on this side. This is electron affinity. Electron affinity times 2 is 2 times 325 minus 325. Okay. So let's see. We're keeping this one here. And we're keeping this one here. And this, let's see. This one is cancels out. These electrons cancel out. I'm just checking myself up to this point. This bromide is taken care of there. And this lithium gas is taken care of there. And this bromine gas. Okay, we haven't done that one yet. Okay. So what we need is bromine elemental gas on this side. 2 of those. So do we have one that puts bromine gas on one side? Yeah. Yeah. So that puts this one and this one, right? Well, I got them out of order. This is HBr. Yes. That takes care of that one and that one. Now we need 2 of those. And the bond energy for HBr is 363 times 2. Okay. Excuse me. Let's see. That one's gone. I normally would draw a line through them, but I think that would be too confusing. This is confusing enough. So we've got these 2 hydrogens here separated. And we need a hydrogen gas on this side made out of two hydrogen gas atoms. So that's the bond energy of hydrogen, isn't it? Only it's reversed. Okay, so the bond energy would be 432. We need minus 432 times 2. What? No, just one. Just one. Because all we did was reverse this one. Okay, so that takes care of that one, that one. That one is canceled by this one. Okay, we have any that are not checked or underlined? Check, underline. Yeah, yeah. Okay, everybody's there. So now we just have to add those up. Unless I made a huge mistake somewhere. So 809, change the sign times 2. And 166. 2 times that one, add that in there. 520, which is 1040, isn't it? 1040 plus. And then 325 times 2 is 650 minus, and 363 plus, and 432 minus. So I get minus 602 kilojoules. Okay, that's a lot of work. A lot of work to get that value. That was 51. In the interest of time, I'm going to have to skip the next one and let you, I think it may be on a previous video, or you can just study it from the worked problems. But we work it the same way. It's a Hess's law problem, number 52. Okay, short answers. All right, we are getting close to the end. And if we have time, we'll come back to that one we just skipped. So in spite of the large electronegativity differences between bonded atoms, beryllium dichloride has no dipole, while sulfur dichloride does. And explain why. Okay, we did beryllium chloride before. Beryllium chloride. Like that. Okay. This has a dipole there. This has a dipole there. Equal and opposite, they cancel each other out. That's a nonpolar molecule. Whereas sulfur dichloride, I'll have to draw that one. Yeah, might as well do that one. So this is 6, and that's 2 times 7 is 14, so there are 20 electrons. Sulfur in the middle, chlorine, chlorine, 16, 2, 4, 6, 8, 10, 12. 4. There. All right, we see some similarities there between that and water. It's going to be tetrahedral electronic geometry, but bent. So if it's bent, that means we would draw it something like this. And lone pairs up here. So which way is the chlorine's to the right of sulfur, so it's probably that way for the bond polarity. But these lone pairs up here draw it that way, so I'm not sure which way it would go. Whether it would go this way or that way. Anyway, it is polar, because these are polar bonds that are unbalanced in the geometry. And I put it in those words. I didn't subscript the twos. I think this is an old document. I know how to do that now, but I just didn't change it. Okay. 54. All right. We've got this compound, iodine tetrachloride ion. That. And we want to know three things: Lewis structure, molecular geometry, and polarity. Okay. So we have 5 times 7 is 35 plus 1 equals 36 electrons. Okay. Iodine is going to be in the middle because it's below chlorine. And we have chlorine, 2468, which was 28, right? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Is 4. Goes there, there. Okay. 6 groups around iodine. Electronically, it's tetrahedral. When we have lone pairs in a, octahedral. Octahedral. When we have lone pairs in an octahedral arrangement, they go at the apexes. So if we drew the center square, iodine in the middle, then we would put the chlorines here. And lone pairs up there. Down there. Okay, so and don't forget charge. Now I drew these with organic chemistry conventions. When we do that, we say, if you turn that flat, then the bonds that are coming out of the board are the solid wedges. Call it dash wedge notation. These would be like that. That. And these would be that, showing going into the board. That's why it's drawn that way. And this would be nonpolar molecule. It would be, but that would be the Lewis structure. It'd be nonpolar, and it would be square planar. Okay. The mistake that students make most often, if they forget that there. Okay, that's it.